Let's go through the steps of finding confidence intervals. The one that we are going to go through now is called the one mean z interval procedure. So the purpose is to find a confidence interval for a population mean mu. Now, in order to be able to use this particular procedure, which is called the one mean z interval procedure, certain conditions need to be met. The first one is that the results of our finding should come from a simple random sample, and that is going to be true for all our studies. If the sample is not simple random sample, that means it is not a statistical study. Number two, it has to be a normal population. So it should represent a normal population, or the sample size should be large. So normal population or large sample. In the next slide, we will talk about what is considered to be a large sample. And finally, and the most important criterion is that sigma should be known. Now, sigma is the population standard deviation. So in order to use the z interval procedure, we must know the population standard deviation. If it is not known to us, we will not be able to use this procedure. We will have to use a different procedure, right? Given that all these assumptions are met, let's go through the steps. Step one is for a confidence level of 1 minus alpha, use the table, or you can use your calculators as well. If you have a statistical package on your calculator, we need to find the z of alpha by 2. So we have to find the z value, whose area to the left is alpha by 2, or it could have an area on the right hand side too, which is alpha by 2. Step 2, the confidence interval for the population mean is calculated from using these formulas. X bar, which is our sample mean, minus z of alpha by 2 multiplied by sigma divided by square root over n. So to find the lower end, we do a subtraction from the sample mean, and to find the upper end of our interval, it'll be x bar plus z of alpha by 2 times sigma divided by square root over n. So these two, which are essentially the same formula except one has a minus in it and the other one has a plus in it, will give us the two endpoints of our interval. And then finally, step 3, we will interpret the confidence interval and relate it to the problem that we are studying. Now, what I'm going to do is I'll just draw a standard normal curve and explain the steps one more time using the curve. So previously we said we will have a standard normal curve, a symmetrical curve, and if we want to find the confidence interval, the interval will be at a certain percentage, correct? The confidence interval is qualified by a percentage value. And then the end point of our interval will be around the sample mean, exactly at the middle of the standard normal curve. And these endpoints will cover an area under the curve. And I'm going to shade this area, which is the decimal version of whatever percentage we are using for our confidence interval. All right, so let's say we are using a 95% confidence interval. In that case, the area bounded by the endpoints of our interval is going to be 0.95. So we convert the 95% to decimal, and that's the area that is bounded by the interval we are going to find. Correct? It also means that the probability that the population mean is going to be within this interval is 0.95. Now in the next step, we need to find what the unbounded area is. So we said the unbounded area is the sum of the area at the two ends of the curve which are not shaded, right? And we denote that with the Greek letter alpha. That's the unbounded area. And how do we find alpha? We do 1 minus whatever the confidence level is. So 1 minus 0.95 in this case. So alpha is going to be 0.05. But that's the areas of both ends together. We need to find the area at each end. So on the left hand side as well on the right hand side. In order to find those areas, to highlight maybe this blue area is the unbounded area, falls outside our interval. So that area can be found by dividing alpha into two equal parts. So this area is going to be alpha by 2, so 0.025. That's alpha by 2, and so is the area at the right end of the curve. It's going to be 0.025. How did we get 0.025? We just took our alpha and divided it into two equal parts and we got 0.025. So far we have only found alpha by 2, which is 0.025. We have to find the z value corresponding to an area of 0.025 on the left hand side, as well as the z value at the upper end of our interval whose area to the right is 0.025. We have to use our table to find that, and if you look up the table, it'll be a negative 1.96, right? So I'm going to write negative 1.96 on the left hand side and a positive 1.96 on the right hand side. Okay, so those will be our z of alpha by 2 values. Once we find a value for z of alpha by 2, in this case z of 0.025, we go on to the next step where we just apply these formulas. We just plug in a value for x bar, which will be given to us. We have found z of alpha by 2, 1.96. We will be given sigma, and we should also be given the sample size. So we apply these two formulas to find the endpoints of our interval. And then once we get those values, it'll give us a confidence interval starting from this point to the point at the upper end. And in the final step, we'll just go and interpret the confidence interval. So when we work through some examples, I will tell you exactly how we expect you to interpret the confidence interval. Now, when we were going through the steps of the z-interval procedure, there was an assumption which said that the sample must either represent a normal population or it must be a large sample. What is considered to be a large sample versus a small or a not so large sample? This slide is going to explain that, so I'm going to read through it and try to understand what are the rules for sample size to be considered large enough to assume that it's going to have a normal distribution. So it says here for small samples, say of size less than 15, so when the sample size is less than 15, the z-interval procedure should be used only when the variable under consideration is normally distributed or very close to being so. So either they have to tell us, if the sample size is small, that the variable is normally distributed. The question should tell us that, or we should know from previous studies that it's normally distributed, or we can go through the process of creating a normal probability plot and decide from there whether the variable is normally distributed or not. For samples of moderate size, say between 15 and 30, the z-interval procedure can be used unless the data contain outliers or the variable under consideration is far from being normally distributed. So if it is a medium-sized sample between 15 and 30, then we can use the z-interval procedure provided the data does not contain too many outliers or the variable that we are studying is absolutely not normally distributed. It has a completely different distribution. All right. In those cases, we shouldn't be using the z-interval procedure. And then for large samples, which is size 30 or more, the z-interval procedure can be used essentially without restriction. However, if outliers are present and their removal is not justified, you should compare the confidence intervals obtained with and without the outliers to see what effect the outliers have. If the effect is substantial, use a different procedure or take another sample if possible. So what they are saying is, if the size is 30 or higher, then you can really go ahead and use the z-interval procedure, pretty much assume it's going to be normal distribution, even though you don't know how the variable is distributed. But if you see your data contains outliers, then you should create two confidence intervals, one including the outliers in the sample, and another one excluding the outliers, and see how they compare, how much effect the outliers have on the intervals. If the effect is substantial, then we just cannot use the z-interval. If there's a lot of difference between the confidence intervals, including the outliers versus excluding the outliers, then we will just have to use a different procedure. And then finally, if outliers are present but their removal is justified and results in a data set for which the z-interval procedure is appropriate as previously stated, then the procedure can be used. All right. So the bottom line is that a sample size, when n is 30 or more, then we can consider the sample size to be large enough to use the z-interval procedure, provided there aren't too many outliers in it. All right.